Hi everyone. In the last two lectures, we started off our discussion on the voltage comparator circuits. We looked at the schematics of commercial voltage comparators like the LM393 and then compared it with the popular 741 op-amp IC, and then we saw what are the differences between the two ICs. Now why did we do that exercise? That's because we said at its heart a voltage comparator is a very high gain differential to single-ended converter, single-ended amplifier. Okay, so then an op amp is also by definition a similar structure. It also takes a differential input and produces a single-ended output, which is a hugely amplified version of the input differential voltage. So then why do we need a separate commercial IC for comparators? And we argued that for comparators, you can realize the comparator using very high gain stages and not worry about compensation, whereas for a 741 op amp, compensation capacitors are mandatory because they will be used in negative feedback and therefore we have to stabilize them. Now when we were looking at the schematic of the 393 IC, we said the schematic made total sense because the first stage happened to be a very high gain common emitter, PNP transistor based common emitter amplifier. It was a differential to single ended converter. Then we had a cascade of three-stage common emitter amplifiers. Okay, common emitter, a common emitter, and then a common emitter finally. Now, this made total sense except the first stage. Why do we need this common collector first stage? When a common collector stage, we know that it's not going to give you any voltage gain, right? The maximum gain of a common collector amplifier is 1. Then why do we need a common collector amplifier in the first place? I said in the last lecture, we'll try to understand and give a reasoning for this in the upcoming lectures. So in this lecture, we'll try to understand why is this common collector amplifier present. To understand why is it present, we have to understand a very important problem that is specific to the voltage comparator circuits. And that problem is called kickback noise. So what is kickback noise? So to understand what is kickback noise, consider an inverting comparator where we are feeding an input signal with a finite source resistance to the inverting terminal. So why did I call it an inverting comparator? Because I'm feeding my input to the inverting terminal. So if your input is greater than Vref, your output will go to minus Vsat, or if it's a unipolar op amp, it will go to ground. If your input is less than Vref, okay, your output will go to plus VDD, okay, or plus Vsat. So if I'm going to assume that this op amp, this comparator is a unipolar op amp, which means it operates between ground and VDD. The minimum voltage level is 0 and the maximum voltage level is plus VDD. Now we'll for simplicity, we'll assume our input signal is a slowly varying slowly varying triangular waveform. So in one half of the cycle, it's going to increase slowly from a lower value to a higher value, and in the other half of the cycle it will decrease from a higher value to a lower value, and the threshold voltage Vref is somewhere in between the lower and the higher voltage levels. Now let's consider this area where your input signal is slowly decreasing and it has just crossed Vref in this direction. So which means your input signal has become slightly less than Vref at this point. The moment your input signal becomes lower than Vref, what should happen to this comparator circuit? The comparator's output should go to plus Vsat. Since it's a unipolar comparator, I'm going to assume it starts at 0 and suddenly goes to plus VDD. Now let's assume there is a finite coupling capacitor between the output node and the input node. Some coupling capacitor Cc between the input nodes. And the source resistance is assumed to be Rs, and we'll assume that the input capacitance at this node, at the input node, is C1. So if you look at this circuit, I'll draw this separately. So this is your output node. You'll have the output node, a capacitor Cc, and then you have at the input port the source resistance Rs and a input capacitance C1. Now this node voltage V0 is seeing a sudden excursion. Remember, input is changing very slowly. It's changing very slowly compared to the output. Output, it's a high gain comparator, a high gain amplifier, so output can change very fast. It suddenly goes from 0 to VDD. So what happens when I apply a step input at this node? What will happen to the voltage at this node? This happens to be your input terminal, okay, or the inverting terminal of your op amp. What happens to the node voltage at this point? It will also see a sudden step change because there is a capacitive division. So suddenly at very high frequencies, so the instant when the step change happens, I can assume that the parallel RC circuit will look like purely a capacitor because your capacitive impedance will be very low at high frequencies. So it will look like a capacitive divider, and if this node voltage goes from 0 to VDD, your input node voltage will also jump by an amount given by Cc by C1 plus Cc times delta V. Here I've assumed VDD, so it will be Cc by C1 plus Cc times VDD. That will be the voltage jump. Suddenly this node will experience at the time when the output transitions to VDD. So it will suddenly go to VDD. It will go to some change. Let's call that delta V, where delta V is given by Cc by C1 plus Cc times VDD. Then this resistor Rs will slowly start discharging it, and eventually it will bring it down to 0. So what will be the voltage across the capacitor Cc in the steady state? It will be VDD itself. So the capacitor Cc will eventually store a voltage of VDD. But the input node, the inverting terminal node, suddenly saw a voltage excursion, and then the voltage died down. So what's happening here? I've drawn the input. This is your input waveform crossing your reference voltage, and I'm plotting the voltage at the inverting terminal of the op amp. See, that's what matters, right? If your V plus is less than V minus, your output will go to if your V plus is greater than V minus, your output will go to plus VDD. Now what's happening to V minus is that because your output is suddenly jumping from 0 to VDD, your node voltage V minus is seeing a sudden excursion to a sudden jump in the voltage by some delta V units. And then the resistor will slowly discharge it, and it will go down to 0. Once it goes down to 0, then the inverting terminal will follow the input signal itself. So at the inverting terminal, there are two voltages that are trying to determine its node voltage. One is the input signal, which is connected to the source resistance, and the other is the output signal, which is connected through a coupling capacitor Cc. There is no DC path, but there is a transient path due to a coupling capacitor between the input and the output. Now if you notice this, your inverting terminal node voltage had suddenly gone even above Vref momentarily. For a small duration it had gone up. So what will happen? The comparator will think its differential volume. See, at this point this is your V minus. V minus has gone greater than V plus. V plus is at plus Vref. So if V minus is greater than V plus, then your output will go to 0. Okay. Then as your inputs is slowly decreasing, what will happen? The opposite will happen now. Your output will suddenly go to 0, and your capacitor will couple back a negative voltage to the input. So you will see a sudden negative spike. And since you see a sudden negative spike, your output will again go back to VDD, and again you will see some till the point where your input moves far away from the reference voltage. At that point, even though there are jumps, those jumps will no longer impact, right? The jumps will be still beneath Vref. So it will not change the polarity of the output. So till some point, until your input signal is farther away from the reference voltage, your output levels will not be stable. It will keep oscillating between 0 on VDD and 0 on VDD and so on. This problem is called false triggering. And this false triggering happens because of the voltage kickback. The output voltage coupling to the input node voltage, which again changes the decision of the comparator. Okay, so this problem of voltage kickback can lead to false triggering, which means the output of your comparator will not be stable for some duration. And especially it becomes a serious problem when your input signal is changing very slowly compared to the rate at which your output changes. If your input signal is changing very slowly, this becomes a serious problem. So I'll first show this problem at a schematic level. I just assume there is an input capacitance there is a coupling capacitance between the output node and the input node. Where does this coupling capacitor arise? So here I've shown a simplest realization of a comparator using a common emitter, differential input to single-ended output amplifier. So here input is applied to the negative input. So this is your inverting terminal. This is your non-inverting terminal where we have applied Vref. And your input signal is slowly decreasing. It has gone lower than Vref. So this output will suddenly go high from 0 to VDD or whatever, from lower voltage to a higher voltage. What will happen? It will directly couple through the base collector capacitance at this node. It will couple through to the input to the inverting terminal through this base collector capacitance. So that's what causes a jump, and then it will lead to false triggering, and your comparator's output will not be stable for some time, okay, until your input signal becomes much smaller than your reference signal. At this point, after some point your comparator's output will stabilize. Okay, so is there a circuit way of fixing this problem? Can we fix this problem of voltage kickback? One simple way of fixing this kickback problem is just to insert voltage buffers between the input signals and the differential amplifier. So you'll have the input signal, let's call this V plus and this is V minus. Before they are being fed to the high gain amplifying stage, we will pass them through a voltage buffer. What is the definition of a voltage buffer? It acts like a unilateral amplifier with a very low output impedance. If the impedance at this node becomes very low, then if you see, you have a coupling capacitance which will then see a very low output impedance, of the buffer, which will appear as the impedance. Let's call this node voltage as let's call this node voltage as 1. It will be Z1 will be the impedance of this node, which is much lower than the input impedance. So, right, previously input impedance was some capacitance C1 in parallel with the source resistance RS. Now we are assuming it is much smaller than that. If this impedance is much lower, then the jump at this node, the switching that happens at this node will also be much smaller because of your kickback noise. The jump in the voltage will also be much smaller. If this jump is much smaller, even if there is any coupling gap between the buffers input and output, it will appear as even smaller variation at this input port. Okay, so the main goal is that adding a buffer decreases the input impedance at this point. Therefore, it decreases the magnitude of jump significantly. If you put an ideal buffer, this jump will become almost zero. It will have no jump at all. This jump will just be plain zero. Okay, I'm sure ideally I should show it at this node, but it just works here as well. I'm just trying to illustrate you the problem is fixed by adding a voltage buffer. How do you realize a voltage buffer? The simplest way of realizing a voltage buffer is using a common collector amplifier. A common collector amplifier is a voltage buffer which will provide you a very low output impedance, which is close to 1 by GM, and therefore it can significantly decrease the voltage jumps at the inverting terminal node. So what I've shown here is an NPN transistor based implementation. It's a NPN transistor based common emitter differential to single-ended converter and an NPN transistor based common collector configurations. What we saw in the 393 IC is a PNP transistor based common collector and a PNP transistor based common emitter differential to single-ended amplifier. Okay, but the concept holds true. It's the same reason why it was added, and the reason was to reduce kickback noise. So kickback noise, to summarize, can lead to false triggering. Your comparator's output will not be stable even if your input goes lower than the reference signal, the threshold voltage, for some time. To avoid that problem, we have to decrease the voltage that is the kickback voltage at the differential input pair. And to decrease that, we just added a common collector configuration. Right? Common collector configurations are famously known for their very low output impedances. That's the reason for adding a common collector input stage, right? So even though it's giving a gain less than 1, the main reason is that it adds a very low output, so it decreases the inverting nodes impedance, and therefore it decreases the kickback jump, okay, which in turn reduces which in turn makes the comparator's output stable. Okay, thank you.